Okay, the reason I'm going to talk about finite state machines is that most of the rest of this semester, we got about 4 weeks left, is what I understand, 3.5, 4 weeks of lectures. I'm going to probably be doing labs for most of those. Because really today is going to kind of wrap up most of what's going to be on the final exam and what's on the syllabus. So, and the reason I've done that this way, the folks are finally arriving. I figured if I started lecturing, they might show up, right? Okay, quote your name for the record. Everyone who walks in late, that's there. So, okay, let me start over again. I'm switching gears today a little bit, and I'm going to talk about a subject called finite state machines. Now, finite state machines is not a subject that's unique to microprocessors. Matter of fact, it's quite often not included in a microprocessor course, but it's a general technique for designing systems of control systems out there. You probably had a little bit of that in your basic digital course that they talk about finite state machines right there. So I'm going to kind of go through finite state machines, and I'm going to kind of wrap up with an example of one where we would use it for a microcontroller project that there, and I'm going to use it in C more than assembler. We could do it with assembler, but it's not as easy as do it with C. So, all right, right there. Let me just jump into my slides. Right there. And here is the rest of our crew. I wouldn't say the rest of our crew, but right there. I've got a series of slides I'm going to go through, and they're like any other series of slides that I've used. I tend to deviate quickly from them that there, but they kind of hit that there. So it's an approach when we look at, where's my function key right here? Function. When we look at a state machine, first off, let me talk about what a state machine is right there. It's an integral part of software programming. In other words, it's part of programming. When we look at state machines, from the viewpoint I'm talking about, it's more of a programming technique. But what is a microprocessor? It's a IC, digital IC, that we write software for, right? 90% of what you use a microprocessor for is writing software. You know, we spent the first 3 or 4 weeks, maybe 5 weeks, looking at the hardware. Your final exam is going to include a lot of hardware discussion that there's there, I keep pointing that out there. But when we look at microprocessors in the real world being used, that there, 99% of the work done is in the software realm. So, and the next semester actually gets into a little bit more of the software, but writing software is where things really happen. We can buy a microprocessor board that does everything we want to do. If you look at the board that we use for our lab, it's a little tiny board that we plug right into a programmer. You know, we can take that board, put 3 volts and ground to it, and stick it into any system that there. In other words, designing microprocessor systems from a hardware standpoint is actually fairly easy. You know, you look at it, look at the data book, and it perfectly gives you the schematic of any configuration right there. You can buy a Raspberry Pi development kit. That's a full micro computer actually on a single board the size of a credit card. I brought one into class a while back, right? Up there, up there. You can use the Arduino microcontroller development kit. Those can be purchased for like, I think they're like 50 ringgits, 45 ringgits, something like that. They're very inexpensive. It's the entire programming kit, and then you tie everything to the outside. So the hardware part of the microprocessors is really the easy part. That there, and you may not think so sitting on this side of the room when you look at all that discussion of ALE lines and where that ties to, and address encoders and buffers and all that. But really, that's the easy part, because that's fairly straightforward. It's developing the software to make things happen out there. So again, we're looking at this here. You know, it's an integral part of programming. 90% of all control applications that we would see with microprocessor-based systems can be done doing finite state machine approach. That's why I'm sticking it in the end of this course here instead of waiting until next semester. They're not just limited to firmware. You can use them for anything. You had them in basic digital. I teach finite state machines and doing VHDL design, which is designing custom ICs to do embedded systems. Any embedded system can be done with just a few exceptions with a finite state machine. So this is going to look at that there, and I lied on this slide. I'm not going to do it in the somewhere. I started to write these slides and then I said, no, I'm not going to do it in the somewhere. I'm going to do it in C, because C is so much easier. And remember, we spent all of our software time using assembler, right? Not there. And then in reality, assembler is great for understanding the inner workings of the processor. It's not so good for doing real work. But there. So what is a finite machine? That there. Yeah, I'm probably going to jump out of here to go through an example. A finite state machine is basically you have a finite number of states. I'll give you an example. A washing machine. The ladies probably know washing machines better than the guys do, right? Any of the guys ever here touch a washing machine? You know what a washing machine is? It washes your baju, your clothes. What? Muscle? Yeah. But it makes you wash, it washes the clothes. So you put the clothes in the wash machine, right? It can't do that for you. Then you hit a button, right? And the button starts the washing machine. Now the washing machine, if it's an automatic washing machine, runs by itself, right? It goes through a number of steps. I'm going to call these steps states. What's the first step that your washing machine does? It fills it up with water, right? So that's state number one. It fills it up with water. And it does that based on, it opens a valve, the water comes in, and then there's a sensor somewhere in the machine that tells it it's full of water, right? So that's state number one. What's the next state? What does it do next? It washes. It sits there and it turns that little motor that just shakes the clothes up and bounces your dirty clothes in the water and gets all the dirt out of the clothes back there. And it does that for so many minutes, right? So you've got another state, the wash state. What does it do next? It drains. It opens the valve and all the water goes out the wash machine into a hole in the floor. Hopefully you put the hose in the hole in the floor. Otherwise you got water over your house, right? So you've got this wash machine. It's got the drain. And then it goes to the next state. Once all the water is done, it spins around, right? It just spins for so many minutes in order to get to whatever water is still up in your clothes back there. And then what does it do next? It fills back up with water to rinse the clothes, right? Because you wash the clothes, it's filled with, the clothes have now got all this soap in it, and you got to get the soap out of the clothes. So you need to go through the rinse cycle. So you fill it back up with clean water. So as we look at this here, and I'm going to just jump out of here, and let's just kind of go through what happens in a wash machine in terms of states. Now we'll talk about right there, here, and I pick on the guys because most guys I know here in Malaysia almost never wash clothes. Do you? You take it to the what they call Dobie. The Dobie is the washing machine. All the ladies, your mother's taught you how to wash clothes, and you probably had to wash clothes for your brothers and your dad. So the ladies are more familiar with the washing machines. That there. Okay. Well, let's kind of go through our states here, and let's just kind of talk about the first state. Our first state is we're going to fill it with water, right? And when we fill it with water, a number of things happen. And I'm going to kind of put this underneath here. First thing is we're going to close the drain valve. Right there. So we know that when we're filling it, we don't want the drain valve to be open. Otherwise, as we put the water in, it just goes right out the bottom of the machine. So we need to close that. We need to open the fill valve. So we need to open the fill valve, right? And we probably need to turn off the motor, right? Motor. Right there. So those three things happen while we're in the fill cycle. Now we stay in this fill cycle until full is 0. In other words, until our sensor tells us that we're full of water, we're going to stay in this fill cycle. Now once we get done with the fill cycle, we're going to go to the wash cycle. Right there. Now our wash cycle, again, we're going to have a few things. Again, we're going to keep the drain valve closed. I'm going to call it DV from there on out. At there. So we're going to close the drain valve. Right there. And I'm going to abbreviate that. Close the drain valve. We're going to close the drain valve. We're also going to close the fill valve right there. You know, it's already full. We don't need to fill it up with water anymore. And at this point, we're going to turn on, and I'm going to call it, if I use the term agitate motor, does that mean anything? Or we'll just turn on motor to wash, okay? Turn on wash motor. When we look at a washing machine, the motor has three different modes of operation. Right there. A washing machine motor has three different modes of operation. One is the one where it's washing, where it goes back and forth, right? That's the one where it's washing. The second mode of operation, it goes very fast and spins the clothes. That's there. And you can probably guess I worked on washing machines for Whirlpool on a couple of projects. That's there. I didn't work for Whirlpool, but I worked for a consulting company, and we did a couple of projects for Whirlpool. So I know washing machines better than I care to talk about. It's just that there. So when we look at a wash motor, it actually has two different motors windings in there. One is the mode that does the agitation, and you put it in that mode. It's got a transmission that just switches direction. So from our microprocessor standpoint, or our digital IC standpoint, that's a signal output that we take high, and we're putting this in the wash mode. Right? The second mode is the spin cycle mode, and that's the one where it goes really fast. So when I turn on the motor, I have to tell it which way I want to turn it on. Do I want to turn it on to wash, or do I want to turn it on to spin dry? Right there. So we've got the spin dry cycle. So we do this right here. We close the drain valve that there, and we do this for a certain amount of time. And I'm just going to say right here, this is our time delay equals 0. In other words, we have some other routine that we call it to simply delay our time. And we talked a little bit yesterday about using the timers and things like that. But we're going to say we're going to put this in a mode where it's going to wash, say, for 12 minutes, 15 minutes. Now, if you look at modern washing machines, the wash time is programmable. Right there. We just bought one just recently, a automatic washing machine, and we can tell it to wash for 12 minutes, 18 minutes, 20 minutes, something like that there. So when we look at our washing machine, this is like anything else, this is a very low-cost washing machine because we're designing it as a second-year students or third semester students. We're not going to worry about having a full menu of options. So we're just simply going to say that it's got to be single wash time. That's it. And we'll talk about setting up this wash time later. Once we get done washing, right there. We're going to then go into our drain mode. And I'm going to call it drain 1 because we're going to have 2 drain modes, right? We could have 3 drain modes depending on how smart we want to make our washing machine. Right there. But our drain mode, all we're going to do is we're going to do that until it's empty. Equals 0. And at this particular point, we open the drain valve, we close the fill valve, and we turn off the motor. Motor off. Now, I'm writing these here down. These are what our outputs are going to be. Now, it might be easier when we think about our finite state machine design to leave this part out until later. Right there. So, but we're going to go through and look at this right here. But we're going to sit there and we're just going to spin this, or just going to empty the washing machine out right there. And then we go to our spin 1. Here we stay there for, again, our delay. And I think you get the idea of what we're doing here in terms of, how I'm taking something very simple like a washing machine and I'm putting it into states in order to because our next step is we're going to design the software to run this washing machine right there. And that's where ultimately what are you going to use a microprocessor for, right? You want it to do something right there. And in this particular case, we wanted to run this washing machine. So this is kind of bringing it back to where it's something useful. That's why I'm sticking this lecture in toward the end, is now we can see what we're trying to accomplish with our processor. So let me go back to my slides here if I can. Right here. Again, function. Right there. Let me get this stuff. Okay. All right. Finally, based on the idea of there are a finite number of states for our system. So I gave you an example here when we look at our washing machine that we've got a number of states. Now, I have not gone through and defined all of our states for our washing machine. We'll probably come back to another example. This is an example that I copied here. It's an application turns on LED on or off. Blinking is a state machine. One state it's the LED's on, the next state it's off. The one that I gave example is the washing machine is a much more complex finite state machine. It probably, by the time we're said and done, it's probably going to have 10 or 12 states. Right here, blinking. Another example, 8 LEDs. A counter is a finite state machine. You count from 0 to 9 and start back to 0 again. You've got 10 states right there. So these are all that there. So this here is one LED. There. Each state consists of one LED turned on while the rest are off. So anything here that you want to do, a counter, a washing machine, driving controlling the engine on your automobile, it's got various states. Now some of those states may have variable outputs. So in other words, you may have to read, for example, a sensor which is telling the position of the gas pedal to know how much fuel to pump into the engine, which controls the speed. But a car engine's got basically, 3 states. One is sitting off, the other is sitting idle, and the third it's running with the transmission engaged. And of course, the transmission is also finite state machine. It's either drive, park, reverse, idle, or neutral. See, these are all finite state machines as we look at that right there. So, what is a finite state machine? Usually, we define a state variable. Again, I'm leading you to the idea that we're going to write software. So software has variables too. You've taken a course in C, right? You know, at least you're shaking your head, yeah, yes. Other people, so I've had classes that have said, no, I've never seen C before. I've looked at your curriculum. You've had C before you've had this class. Out there. Some of you have had programming in other languages, such as BASIC in high school, out there. But you understand what's meant by a variable. We're going to declare a variable as a state variable. What it's going to contain is all the allowable states that we could be in. And we have to be in the, keeps track of the state that the microcontroller is in and directs the flow according to the software module. In other words, we're going to say what state we're in and then what state we go to next. So those are the key things that we're looking at. Every state has a unique set of outputs that are there. The state variable can be modified in the software, the states themselves provide an outside function. In other words, we can have outside things right there. So, an example, you know, and everyone understands the term firmware. I'm using the term firmware. Firmware is software that we put into a microcontroller system or a microprocessor system that we program onto the chip. Right there. When you write your software for the labs and you download it into that little board, that's firmware. You unplug the board, that software stays there. So it's firmware. Software, as you think about for a desktop, is on a floppy disk. That's where the term came from. I know floppy disks are obsolete. Has anybody here ever seen a floppy disk? Right there. Back in my day, floppy disks were actually inside paper sleeves. You could bend them, and they were actually floppy. Right there. That's why we call it floppy disk. You know, when I first started, they were 8 inches in size. Right there. And then they became 5 1/4 inches, and they were still floppy. And then they became 3 1/2 inches, and they were inside hard plastic. And then they just completely went away. Now, do these computers have floppy disks on them? No. Yeah. I actually have an old computer at home that still has a floppy disk slot. See that there? So again, the term software typically came from the idea that it came on a soft block. Back there. And then firmware meant that it's not really hardware in the sense that when you look at the microprocessor and you look at the memory and all the ICs, that's hardware. You can touch it, you can feel it, you can see it. Firmware is actually software that we program into our ROM chips back there. It's not really hard because we could change back there. But it's firm in the fact that whenever we power down and power back up, it's still in there. The operating system in your phone, for example, is considered firmware, right there. So when we look at that there, now there's an example of firmware can use an outside function to detect a button press and advance through the state. What did I do to start the washing machine? I pressed the start button, right? I'm in a state, I turn on this washing machine, and it's sitting there looking at me, and it does absolutely nothing, right? It's doing absolutely nothing. I can leave it turned on all day, and it doesn't do anything. I can put the clothes in it and go eat lunch, come back, my clothes will not be washed. Why? I haven't hit the button to tell it to move into the fill mode. It sits there in this idle mode until the start button is pressed. So we have inputs that there. Now we typically look at a model right here, and this is one drawing that there. I typically don't use it this way. You typically look at another model right here. Right there. There's various models, but we'll look at this one here. This one's perfectly fine. What we have, this is kind of a flow chart here, is that we have some logic that we're going to write. And we're going to just use a select case statement in C for this logic right here. Right there. Then we have our state variable. Our current state is what's coming out of our logic. In other words, what state are we in? in every pass through or every clock cycle, we're going to look at our current state, we're going to look at our various inputs coming from the environment, and these can be push buttons, they can be timers, they can be anything right there, but these are inputs coming up there, and we're going to determine what our next logic state is. So we've got we've got a list of states that we can be in. We've got this whole list of states. We know what our current state is. That's important. We know what our current status is. If you're driving from Kuala Lumpur to Johor Bahru, it's important to know where you're at, right? And then we have to decide where we want to go next. Sometimes we want to stay right where we're at. You know, if we're sitting there in the idle mode and nobody presses the start button, where do we go next? We stay in idle. You know, no one's hitting the start button. Nobody wants to wash their clothes yet. This machine's just going to sit there and wait. Right there. Or if the start button is pressed, then we progress on to the next state, which is our fill cycle. You know, we're going to start filling this thing up here. So, right there. Now, when whatever state we're in, we have some outputs there. Every state can only have one set of outputs, the way that I teach it. Now, there are ways where you can have a state with different outputs. I prefer to keep my life simple, and that every state has a particular set of outputs. Going back to the example that I gave a few minutes ago, right there. Let me just go back to my example here. Right here. Right here. We have, and I'm just going to list the state here. Idle. Right there. That's a state. That's our initial state, our reset state of our washing machine. Idle. Right there. Our next state is fill. And I'm going to call it fill 1 because we're going to have multiple fill cycles. Now, you could do this however you want, but I'm just going to say outputs right here. Now, there may be more than one output. There may be some LEDs, there may be some other things, but our outputs are going to be motor, fill valve, drain valve. We're only going to have 3 outputs that I'm going to deal with right here. So we got 3 outputs. My motor actually can be, it has 2 possible states. Or I could do it another way. And this is probably an easier way for right now. Let me change this here a little bit. Right here. Let's say for sake of argument that we're going to have 2 motors. One is a wash motor, and the other is a spin motor. So we have 2 motors. Now they could be one motor with 2 outputs or 2 inputs or whatever. We're going to say for right now, just to keep our life simpler, and then we're going to have our fill valve and our drain valve. Those are our 4 outputs right there. So, going back to my previous slide, when we look at for our idle mode, what should our outputs be? Well, in this particular case, we're idling. All of our motors are off, right? Our valves are closed, right? So all of our outputs are going to be 0 right there. When we're in the fill mode, again, it's the same one right here. I'm going to call it wash motor, spin motor, and I can't write today. Spin motor, fill valve, drain valve. In our fill mode, our wash motor is off, our spin motor is off, our fill valve is on right there. So we can just go through and we create a table for all of our various outputs right there for each state. Now, again, the way that I like to do this is that every possible state only has one set of outputs right there. That they are unique for each state right there. Again, we're not getting into how we're going to design this in terms of writing the software. All I'm trying to do is before we can write the software, we have to know what our software is going to do. So as we take our microprocessor and we want to do something with it, we have to look at these types of things right there. So going back to our state machine right here, hopefully this is right here. So what we're looking at right here is that these are our outputs. That's it, to the right of the table. This logic here we haven't talked about, but we've sat there and we've defined all of our states and what the outputs are for each one of those. Then we have to define how we transition from one state to the other. And I prefer to do that as two different types of programs, right? To do that separately within my program. So, that there. Another way of looking at this, and this is kind of a little bit similar to that there. Now this right here, it shows combinational logic. This is a slide that I actually use when I teach VHDL right there. Because VHDL means you're designing hardware. In other words, the output of VHDL or Verilog is a series of AND gates, OR gates, flip-flops right there. It's another programming language. It looks like a programming language, but the output is hardware. I don't think you cover those languages here in your program. Did you, in your basic digital course, did you do anything in Verilog? Does that sound familiar? Okay, well, regardless, that there, we look at that there. But what we've got here is we've got some inputs, we've got some combinational logic, we determine what our next state is, we've got something to synchronize our clock, that's our current state, feeds back, and then our outputs right there. So it's the same type of thing. We're going to be looking at what is our current state, what are our inputs, what is our next state, right there. So the advantages here of using state machines is you're going to pick up good design techniques. What's the difference between a B-Eng student and a B technology student is you're learning design techniques. And finite state machine design is a design technique right there. So when you start thinking about the application, you have to think about what states are required to make things happen. You list all the pieces of the process. This helps you prevent bugs. You go through and you look at your washing machine. What does the washing machine have to do? Right there. I look at a microwave oven. What are the possible states of the microwave oven? Right there. We look at, a traffic light. That's a standard finite state machine example that's used. That there. It has multiple states right there. I've actually taken a course similar to this. That there actually not introduction to microprocessors. Yeah, actually that there. And I started about halfway through the semester and had to do one lab the rest of the semester. It took 8 weeks to do the lab. And what it was a stoplight that just got increasingly more complex. Where at the end of the semester, they had 3 stoplights that are all tied together in a sequence right there. So you can take one application and you can keep making it more and more complex. So you think about that there. So you design the flow chart right there. Now, the flow chart, we're going to, that's there. Usually finite state machines use what they call a state transition table. And I don't know if these slides show one. No. Right there. I don't have that there. But a finite state machine typically would have a, do I have one note here? Yeah, I guess every time we do this, we got to bring this back up here. That there is that we basically come up with here idle right here, and we stay in idle right there, and we would quite often list start. I'm going to abbreviate that there. This gets really messy, but I'm going to abbreviate this here, and I'm going to say start button equals 0 right there. We stay in the start mode until that there. Then we go to our fill 1 right there, full equals 0. Then we go to our wash there, and then we do, I'm going to show it over here, time expired, I'm going to call it TE equals 0. And we'll talk about TE probably in a later class. We probably won't get into TE too much. But TE is a function that we would generate, that we tell it how long we want to stay in a particular state. So it's a variable that we would keep checking. We would use our timer to decrement our time. In other words, we would tell it how many seconds we want to be in there, and then we would set up a half-second delay, and we would load it up with twice that, and every half a second we would subtract 1 from the number of seconds, number of half seconds or whatever. So we would generate a function to keep track of time right there. And then we go from wash, we go to drain 1. And then empty is another variable, 0 right there. And what we're going to do is we simply go through here and we design this state transition flow diagram. And as you can well see, that this is a very sloppily drawn diagram. Mine probably don't get much more complex than this right there. They're fairly straightforward. There's a program out there called StateCAD, and StateCAD is a software package that you can buy. It's relatively expensive. I'm thinking it's in the neighborhood of about $500 to $600 US right there. So you're talking 1,500 to 2,000 ringgits right there for StateCAD. But StateCAD actually allows you to draw this in a much neater fashion. And StateCAD actually does more than that. Is it allows you to draw this, specify these conditions, and then what it will actually do is write your C code for you at the end. Right there. So StateCAD not only helps you draw it nicely, but it also helps you write the code. Or the output can be VHDL or Verilog, depending on what you're targeting. So, but you go through this process right there. Now, some people will do 1 page per state right there. If you do 1 page per state, it would look something like this. Here's state wash right there. And then we would list here, right here, next states right there. We can either stay in wash right there, or we can go to drain right there. And we could actually then go to, and I'm going to call this drain 1, or we can go to another state that I'm making up right now. I'm changing the rules right there, which is not uncommon as you design this. I can go to drain done right here. Somebody hits the stop button right there. In other words, they want this thing to just, they don't want to finish washing the clothes right there. And we can also then go to a wash idle button mode right there. And anybody have an idea why we'd go to it? We would stay in the wash mode, but we stop the motor. Why would we do that? You open the door, right? Most washing machines, you open the door to the washing machine, does it keep agitating? Some do and some don't, right? It depends on where the washing machine was made and what rules are in place. If you go to, say, someplace like Europe that's got very stringent safety rules, you open the door of a washing machine, it's going to stop because it doesn't. They don't want somebody. And they must have some real goofballs in Europe because they got some really strange laws out there. You open the door of a washing machine, they don't want somebody putting their arm in there and getting caught in the washing machine and getting ripped off. And because they have such rules, that means that somebody did that. Right there. You don't make up rules unless there's a reason for making up these rules. So somebody evidently stuck their hand in the washing machine out there and either pulled the socket or did something. So you open the door of the washing machine, you go into this mode where it just stops. The timer stops, the washing machine stops, and it just sits there in a hold pattern. You close the door, it starts washing again. Now not all washing machines here do that. I've got washing machines in the U.S. that do that. I've had them that don't do that, and I've had them that do have that whole cycle. They almost all do that if you've got top-loading washing machine. If you open the door and it's in the spin cycle, right? That your washing machine's spinning, all the water's coming out of it, and these guys are looking at me. Some of you have never watched the washing machine work, right? Everyone has watched the washing machine. You may not fill it, but you've at least seen it work. But if you open the door while it's in the spin cycle, it doesn't keep spinning. No. Except for the one I had that the safety switch went bad, so I just shorted it. And then it would keep spinning. Of course, that would be illegal if I was in Europe. But so as you go through this, you'll find that this machine can get more and more complex as you dig deeper. So today's discussion, I'm trying to keep it simple. So I'm leaving this wash hold out. This wash idle or wash hold is that the abort button. In other words, I hit a button saying that I want this just drained. I need to pull the clothes out. Right there, something's wrong. I put bleach in instead of detergent. So I need to stop this right now and get this bleach out of the drain. So there's all kinds of various options that we can put in there. But these are all the possible next states listed right there. So we would list where we can go to next, right there. And then the next thing we would do is after our watt is right there, TE is equal to 0, right there, and TE is equal to 1. TE is a variable that I made up a few minutes ago, and that's called time expired, right there. Right there. And that's a variable that we'll talk about in more detail later. But this particular variable, when I go into the wash mode, I'm going to start a timer right there. And when I start this timer, it's going to count down how many minutes I want to wash down right there. So sometimes, depending on what you have, is you may have two states internally. One is to start the wash, and then the other waiting for the wash right there. So we may actually have two states. If I'm doing this in hardware, not software, I almost always have to have two states. One is to start the timer, and then the other is to wait for it to, right there. So we have two substates that there. We'll talk about that in more detail. But this is a variable that we would set number of minutes right there. We have some variable that we define within our wash state right there that we're going to tell how many minutes we want to wash right there. And that could be something that we go read from someplace else. It's maybe a little dial that we turn or whatever, the number of minutes. So when we hit the start button, it fills up. And then when it starts to wash, it looks at how many minutes it's going to do, and it starts a timer. And we wait for that timer to expire. Once that timer expires, then we go into our drain. That's our normal mode of operation. These two I just kind of threw out there as possible states that might show up if we were to make this thing more complicated. So our simple one only looks at those two right there. And then along with this right over here, we look at what our outputs are going to be. Now we listed our possible outputs as our wash motor, our spin motor, our drain valve, and our fill valve right there. So when we're in the wash state, we're definitely going to have our wash motor going, right? We're also going to you can't wash and spin at the same time, so we put a 0 there. We don't want it draining anymore because we need the water in there to wash, right? So we shut that there. And it's already full, otherwise we don't do that there. Now I should point out that there are exceptions when you watch it. Has anybody had a wash machine that will spray water in during the spin cycle? That there, I had a wash machine that did that. That there. So, and it does that in order to push some more dirt out there. So there are possible states. Again, these wash machines can get quite complicated. We're going to stay simple right there. So we have a page for each state that we have that there. Now, the way that this is going to work later on is, let me come down here to right here. From current slide. Okay. Again, I'm back to our slides here. So, the benefits is as we go through here, as we think about the problem, we're not even thinking about, memory allocation. We're not thinking about ALE lines. We're not thinking about, relays. We're not thinking about any of the hardware at this point. All we're trying to do is get the process. We're not thinking about how we're going to write the software. We're just defining what the problem has to go through here. So this is actually a very early on design technique right there. So we're looking right here is we're going to come up here with inherently promotes good design techniques. That's what we're looking for. This is a way of designing any type of embedded system where we have control. You think about what states are necessary right there. You list the states. And then you look at how they tie to each other right here. That's where you go from what state to the next state right there. So you come up with the flow chart right there. Right there. Now you do have they always return to one spot in the code. Right there. Jump state right there. This one spot we're talking about in this particular case is the idle mode. This is going to go, we turn on our washing machine, it has a reset state. Our reset is idle. Now idle, we haven't defined. Idle, you may want to have the drain motor, for example, turned on, or valve open. So if you turn the machine off and you turn it back on, if there's water in the machine, you want it to drain. So you think about that, but that's later. That's much later. At this stage of the game, all you define is our idle. We always go back to idle. Always go back to idle. When we're finished washing and we hit that final drain spin cycle and our clothes are ready to be taken out and hung out on the line to dry, or if you're in a cold climate where you don't hang clothes out and you put them into a dryer, you take it out and put it into the dryer. But dryers are not common here, but I do see them sold, so not there. But regardless, when we're completely done washing our clothes, we go back to where? Idle. We reset, we go back to idle. We powered up, down, we go back to idle. So this gives us a place that we always start at, because that's our starting point. It's our idle mode, right here. Calling repetitive tasks are simple. You clear the watchdog timer, you press the buttons, communicate with the host. You just do this in a continuous loop, right there. So now better than loop is use looping code right there. Again, I typically put a finite state machine, I usually just put it within a loop right there. And every time I pass through the loop, I just check everything right there. You could do this at this slide I right here. Okay, we're not used right here. And this is just kind of this is actually not there. I switched it there. Okay, now I'm going to skip that slide. Now let me just jump into a constraint in C right here, right there. And this is the statement. When you took C, did you look at the switch case command? Right there. Because switch case is the perfect way of doing a finite state machine. There. You just switch here, and then you can have your expression. You would typically put your current state in here. So here, case wash versus case idle. What do we want to happen in the idle mode? Well, what we want to do is we want to look at our inputs and determine what our next state is. So this is actually the way we typically would handle. And I do two of these. And we won't get into the details too much of that there. But you would have a case for every possible state in your state machine right there. So if you have 20 that there, you could do this with serious if-then-else statements. And this is the reason why I backed off of trying to do this in assembly. If you try to do this in assembly, you have to use the jump commands that there, and it gets relatively ugly very quickly in assembly. Finite state machines is much more suited to using C right there. You can use other languages, but use the right there. Right there. So this is kind of the way the switch case works, is that we have our expression, and that is, in other words, the expression we're using is our current state. We look at, if we're in this state, we execute this code. If we're in this state, we execute this code. If we're in this state, we execute this code. Normally what you would do in that particular situation is you would just simply look at what our current state is and list the next possible thing. So for example, for our wash machine, and I'll do this on a side note, I don't have that there once I finish the slides right there. But we have something that looks like this right here. Here's a very simple one, and we'll use this as an example to start our wash machine here. This is the way we would normally do our finite state machines in C, right there. Is here we have, we set up an enumerative type right there, and it's called my state, right there. And this particular case, we say that states 1, 2, and 3. We would list all of our states in that list right there. In this particular case, we said that state 1 is equal to 0. In other words, we set that as our default state. And then before we get into our code, right there, we set our current state, and then we declare the variable as state 1. So that sets up our reset state right there. It sets up our reset state. This is just food that there. You know, we're passing it into a current state, switch state right there, and all we're doing is saying, if we're in state 1, if input is true, that there, and we're just saying that there, we go to state 2. If we're in state 2, if input, we go to state 3, else we go back to state 1. And state 3, and we just simply put the code in for all of our various states right there. So if we were to follow this format right here, right there, not there, because this is where I actually ended my slides right here. Right there. Let me just kind of bring up here, and I'm going to kind of wipe. And I guess right here. Right here. Let's look at this a little bit, and again, hopefully, right there. So again, what we're looking at here in this particular case, and again, I'm going to bounce back and forth between here and our PowerPoint, is we're going to look at, matter of fact, let me just cheat. Everyone knows I like to cheat, right? Right there. Control C. So I'm putting that, the reason I put that there is so that I'm going to write on the right side here what I would do for our start the washing machine finite state machine. And I'm not going to finish that there. We're at about 9:30, so we've got a little bit of time here. But we're going to just simply say type definition. It's an enumerated type, which means an enumerated type is a type that you define that has to take certain values. I don't know if it was covered, but when you define a enumerated type, a common one uses days of the week. So you would say Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, for example, days of the week. Right there. So we're going to set a enumerated type, and I'm going to call this type 1, and normally we're going to call idle, right there, equals 0, comma, wash, right there, comma, drain 1, comma, and all the way down. And this is, we would list all of our states there, and we would then call this my states. And you could call it whatever you want right there. Right there. So we've defined a new type in C. Right there. And it's a type called M states right there. You can call it whatever you want. And then we declare a variable right here. Right here. And right there. It's of type M states. And I actually define two right there. And that is, I'm just going to say current state equal idle. Right there. I'll just use that one right there. So all this does here is, this here defines what our possible states are. This simply declares a variable called C state. Now, you won't see M states anywhere else. M states is just, all that does is say what values that current state can take on. Right there. Right there. So that keeps track of what state we're in. Right there. Now, you could do this however you want. Right there. The way I typically do this here is that in my code within main, right there, I have bracket, I have all of my initialization routines. In other words, I set up my I/O ports, I set up my timers, I do all that stuff. That's my initialization stuff right there. Then, after that, I'm going to have a while 1 right there, bracket right there. And inside this while 1, I'm going to have my switch right there. And my switch is going to use current state right there. Right there. We're going to then look at right here. We're going to look at our current state right there. Right there. So that's within my code there. So underneath that there, I have my little bracket there. And I list my first one. Case. Idle. Right there. So now we're going to put all of our code in there for idle. Now, this is just our state transition right there. Now, we go back here, out there, if input, right there, state, out there. The only thing we're going to do in idle is we're going to wait for the push button, right? So we can just simply say if start, right there. We'll assume the start is a push button. If we push it, it becomes a 1. So let's say if we start, right there. If that's the case, we're going to simply C state equal fill 1. Else break. In other words, we're done right there. Again, going back to our example right there, we break. Actually, we don't even need the else there. The else is not even needed right there. Right there. So, break. Right there. And then we go back here, and I keep jumping here, that there, we put our next state in there. Case. Right there. And we continue this on down. That there. That there. And my observer is showing up just as I'm getting ready to finish up. That there. You caught me just as I'm getting ready to wrap up here. That there. So
I have to return. Just
okay, that there. So I'm sorry to wrap up that there. So okay, all right. So as we look at this, our code here. Here, going back to here. This is the example here of doing a finite state machine. There, generic form right there, and we're looking at doing that with ours. That there. So again, as we look at here, there's our 3 possible states. When we look at our example here, and where were we at? Oh, I started here. Right there. Again, we started here, and our first state was idle, and we set that as our 0 state right there. That's our reset state. We listed all of our possible states here. And again, we have not listed all the possible states for our washing machine. We just started this example there. You can see as we're moving on, as we start doing this in a lab, that it's going to get it'll take us a few weeks to go through this here, but idle is where we start, right there. And then as we look at our example right here, here's our while one. Again, this is within our code. Right there, we do our switch. We look at our current state, which is right there. And if our current state is idle, right there, that's our current state is idle. The only thing we're looking at in idle, because remember our state transition bubble graph, where can we go from idle? We can only go one place. We could, the washing machine sitting there empty. We have filled it full of clothes, and it's waiting for what? Someone to press the start button. So if the start button is pressed, our next state is going to be fill 1. So it's that there. If anything else happens in the idle mode, we don't care. Right there. If the time expires, which it should, because our timer shouldn't be running. If the door opens, nothing should happen. If somebody walks up, if they press the reset button, and then of course it's already in idle, it's going to stay in idle. So we don't worry about anything else. We just simply look at the start button there. So our next state we would then go through would be our fill 1. So case. And we'll do one more. We're in fill 1 right there. Right there. So as we look at our case there. And in fill 1, we're if we go back to our example, and I'd have to go back and find it. But in fill 1, we stay in fill 1 until the washing machine is full of water. We have a sensor that we've wired into this washing machine that tells what the water level is in our washing machine. We have some sensor there. Once the water is up to that sensor level, that's going to trigger an input to our microprocessor. We haven't talked about hardware. But we can make assumptions that hardware at this time that we need some way of knowing that the washing machine is full, right? We're at the early stages of our design. So we need to know that there. So if full, and we assume that full is our sensor that goes to a 1 when it's filled with water. It can be a float, it can be a water sensor like that. If that's the case, our current state is going to be equal to wash 1. In other words, we're ready to start washing. No, we're ready to start washing our clothes, right? Now, if we're in the full state, we may have other inputs that we look at there. So we may, I'm just going to make one up here for right now. I'll just say, if else, if, and I'm just going to make one up here at this point. Else if stop, we'll assume that there's a button here called stop, that we want this thing to stop what it's doing and go back to idle. If that's a particular case there, then we want our current state to, and if I'm going to do this, I need to remove the semicolon there, because the semicolon stops the if then else. So if I'm going to put an else on that there, our current state is equal to, and we didn't write this, but I'm going to call it abort. Right there. We're going to assume that we have a state called abort. Right there. Abort. Else. And actually at this point we can just go ahead and break. Right here. And we can break. Right there. So in other words, that handles all the possible transitions from the fill state. You know, we're either full and then we move on to our wash state, or somebody hits the stop button and then we go to our abort state, which we haven't generated. We haven't talked about the abort state, but we're going to assume that we have such a state right there. So any questions on this? Right there. A lot in one hour, isn't it? An hour and a half. That there. We're going to come back to this in the lab and start writing this software. Right there, because this is the way that there. And again, we could go through here and we can look at any type of there. A simpler one. I picked a hard one to start with, but it's one that you can see how it get there. A very simple one, again, is a red light. Red, north, south. Right there. Then we're going to go to green, north, south. Then we're going to go to yellow, north, south. Right there. Right there. And these are the various stoplight modes, you know, on a stoplight. A little bit simpler one there. But it's the same type of process there. Anything that you can put into a control application can be done with finite state machine design. Right there. So we've talked about microprocessors. Now what are we going to use them for? Right there. So with that said, I'm going to stop here at this point. Before I do anything else, though, let me stop the recording before I do the attendance.